I'm Thomas Smith. I'm a technology journalist and the CEO of Gatto Images, and I also have worked in AI for over a decade. And this is Tom Talks Tech, a new podcast where I'll share perspectives on everything in technology and the technology world, from cooking to crypto. Join me here as I explore the world of technology on Tom Talks Tech. I'm Tom, and today I am talking about blue light blockers, whether blue light blockers actually work, and the kind of surprising and interesting brain science behind how they work. And you can read more about this. It's part of my ongoing column, Tech Shortcuts for Life, which is in Debugger on Medium, debugger.medium.com, and that was this week's topic, blue light blockers. I'm a neuroscientist, just a trained neuroscientist, so I have that background, and I'm always interested in seeing how neuroscience intersects with new technologies. And I was thinking about that recently when I was driving through San Francisco, and I saw a billboard for a product called Blocks, which is a blue light blocking pair of glasses. And this is really just sort of the most recent attack in the war on blue light. There was an article in 2018 that called Blue Light the New Tobacco, the Digital Age. So there's a lot of very kind of strong wording around that and hype around blocking blue light. And so I wanted to kind of shed some light, excuse the pun, on the fact that blue light blockers are useful in some contexts, and also they can be harmful in others. And just in general, to understand why there's all of this focus on blue light. So in addition to seeing blue light blocking glasses, there's also features on most modern phones that block blue light and makes the screen more of a sort of yellow or orange tint. On Apple, it's called Night Shift. On Android, it's called Night Mode, and you can usually enable that very easily on your phone. There's also features like on the most up-to-date Amazon Kindle. You can actually choose the color temperature of your screen and make it a less blue, sort of more yellow color if you want to. So there's a lot of different tech tools based around eliminating blue light. And the reason for that is actually that blue light, it's not just all hype, blue light actually has a big impact on your brain and even on functions like sleep and your circadian rhythms and your mood. So why is that? To understand that, we have to look all the way back to the 1920s and a really interesting experiment which showed that mice who are blind, so mice that are born without the traditional photoreceptors in their eyes, are actually able to still have their pupils adjust to light, which doesn't make sense. So they can't see anything. Light hits their eyes, there's nothing being registered in their brain from the traditional photoreceptors, but still their pupils respond to light. And in the 20s, there was some interest in the fact that maybe this could mean there was another photoreceptor that people weren't aware of. And if you remember back to high school biology, there's two classical photoreceptors, the rods and cones. Rods pick up light at very low levels, like at night, if you're walking around a darkened house, or if you're walking around by moonlight. They are black and white only. And cones pick up light at a higher intensity during the day, and they are color vision. So these mice had neither of those photoreceptors, but their eyes still responded. And there was a theory at the time that this could mean there was a third kind of photoreceptor. And that was largely dismissed. It kind of went against the orthodoxy of how photoreceptors were understood. And for almost a century, nobody did anything with that finding, really. And that was until the 1990s when we started to have the tools to actually breed mice that not only lacked the photoreceptors in their eyes, but actually lacked the genes responsible for creating those photoreceptors. So that, lacking the genes means that there's no way they could possibly be creating any of these photoreceptors in their bodies. And the argument before was, hey, they don't seem to have that many, but they must still have a few because their pupils respond. And into the 90s, they started to breed mice where they did not have any of these genes, and yet still their eyes responded, their pupils responded to light. Again, very weird. So scientists actually removed the eyes from mice. And once they did that, their eyes stopped responding to, their pupils stopped responding to light, obviously, since they no longer had them. But something even stranger happened. And that was that the mice started to lose their circadian rhythms. So they would wake up in the middle of the night randomly and start running on their wheels like it was the middle of the day. They'd wake up in the middle of the day and run like it was the middle of the night. And things basically got completely out of sync with the outside world. And researchers studying this noticed that it wasn't just random, actually. It was a pattern where every day their cycles of sleep and wakefulness would drift a little bit. And again, this is really strange. People didn't understand why this was happening. And they started to examine it more, and what they discovered was that that theory from the 1920s was actually correct all along. There actually is a third kind of photoreceptor in the eye. It's called an intrinsically photosensitive retinal ganglion cell. So it's a very, it's a kind of a mouthful, but it's abbreviated as an IPRGC. And these are very different from the classical photoreceptors. They're downstream of the photoreceptors, so they're a little bit further along in the pathway to the brain. And whereas the classical photoreceptors respond to light very quickly, IPRGCs respond very slowly. You have to bathe them in a lot of light for them to start responding, and then once they start to respond, they take a long time to switch back off. So there's different populations of them, but some of them take up to 30 minutes in the light before they start to signal the presence of light to the brain. And they're really not very image forming. There's some theories and research that suggests they might play a role in image formation, but for the most part, they're not signaling the boundaries of objects or the kinds of things that classical photoreceptors would signal. So what do IPRGCs do? It turns out that they're ambient light detectors. So if you are out in the world and there's light levels, it's dark, it's bright, it's nighttime, the IPRGCs are registering that general overall light level in your environment and signaling that to your brain. And the question is, why would they do that? Why do you need to know these levels? And to understand that, it's useful to look at where those signals go. So the classical photoreceptors transmit ultimately to the occipital lobe at the back of the brain, which then passes on their data to parts of the brain that form images and understand objects and help us to see. So that's pretty obvious. They're being used, among other things, for image formation and vision. But IPRGCs actually project to a different place called the SCN, or suprachiasmatic nucleus. And this region of the brain is actually responsible for a lot of sort of basic regulation functions in your body. One of the things that's kind of housed there is your circadian rhythms. So the SCN controls your periods of sleep and wakefulness, the things that vary throughout the day, like when you get hungry, and a lot of other kind of hormonally driven responses throughout the day. Again, like hunger and sleep and basic functions, like blood pressure of your body. And turns out that your circadian clock, which again is in that SCN, is pretty good. Measures out pretty well a 24-hour day. But it's not perfect. It actually varies from the real length of the day by a little bit, and that little bit depends on each person. It could be a little bit fast or a little bit slow. And the problem with that is that over time, if your clock is a little fast or a little slow, think about an analog wall clock that's a little fast or a little slow. Every day it gets a little bit less accurate. It drifts a little bit from the real time. And that's the same thing with your circadian clock. On its own, it would slowly drift over time. And so how does it end up, synchronized with the period of day and night? Turns out that in the SCN, light is used to synchronize your circadian clock with the environment. And specifically, the way that happens is through your IPRGCs. So your circadian clock tries to count out a 24-hour day. It's not perfect. And each day, though, if you spend time in sunlight, in the morning in particular, your IPRGCs detect that ambient light level, and they say, okay, it's morning. And they start signaling to the SCN, hey, it's morning. And the SCN actually resets your circadian clock to match the fact that it's morning and to match the actual period of day and night in your environment. And that process is called photoentrainment. It's really important because what happens if you don't photoentrain is exactly what happened with the mice in that 1990s and later experiment. And that is that if your circadian clock doesn't get synchronized properly to the length of the day, it starts to drift, again, like a analog clock, and you end up like the mice in that experiment where they didn't have any input from the IPRGCs because their eyes had been removed. Your circadian clock drifts a little bit every day and becomes less accurate until you end up totally out of sync with your environment. And you end up like the mice, waking up in the middle of the night, sleeping in the middle of the day, and with a circadian rhythm that doesn't match up with the world at all. So IPRGCs and the input that they provide to the SCN is very important because it keeps your circadian rhythm synchronized to the period of day and night in your environment. The challenge, though, is that that works great in a kind of antiquity type of setting, cavemen type of setting for most of human history, where the only time you'd really experience bright light was during the day. And in particular, the only time you experience blue light is during the day. So it turns out that IPRGCs are perfectly tuned to pick up blue light specifically. And the reason for that is that the sun produces light with a blue tinge. We think of the sun as being yellow or orange, but actually the light that it produces is a very high color temperature. And that means that the light has a blue tint to it. And so IPRGCs are basically sunlight detectors. They're designed to pick up on the ambient level of sunlight in your environment. And again, in ancient times, you only would really experience blue light when the sun was out. So they were very good at doing their job of detecting sunlight. After dark, maybe you'd have a fire, but that would be an orange kind of tinge, a very low color temperature, and it wouldn't trigger the IPRGCs in the way that blue light does. So they're very tuned to this ancient environment, but our modern environment is not like that ancient environment. We are not only exposed to blue light during the day, we actually are exposed to blue light all the time. And we knowingly and willingly expose ourselves to very bright blue light when we pick up a cell phone or a tablet and we hold it right up to our face, maybe at 9 o'clock at night, 10 o'clock at night before bed, maybe in the middle of the night, we're holding this very bright blue light up to our eyes. And the problem with that is, remember, the IPRGCs detect daylight in the form of blue light. So say it's 10 o'clock at night, you hold your phone up to your eyes, it's shining blue light into your IPRGCs, they go, oh, it's morning, great. And they start signaling that to your SCN and then onto your brain. And the fact is that it messes up your circadian clock. Your body is being told that it's morning when it's actually night because it's seeing this blue light, and that messes up your circadian rhythms and changes all kinds of things physiologically about your body. One of the most significant is that it tends to block, to some extent, the release of melatonin, which is one of the hormones required for you to go to sleep. So if you're bathing your eyes in blue light at nighttime, you're actually signaling to your brain that it's morning, you're cutting down on your melatonin, and you can do a lot of other things too. There's evidence that blue light at night can affect mood, can affect basic kind of regulatory functions of your body, like blood pressure, and can cause all kinds of issues. So that's where blue light blockers come in. And the concept is, if you can block the blue light from a device like a phone, even from lights in your environment by wearing a blue light blocking pair of glasses at night, then that will prevent that signaling from coming to your brain and saying that it's morning when it's not. And that should help you to sleep. And there's actually trials, there's evidence that this works. If you wear blue light blocking glasses at night and you switch off, use night shift or night mode on your phone, then there's actually evidence that that will increase the amount of melatonin your body produces and result in better sleep. It's not conclusive, but there is some really good scholarship and evidence around that. So surprisingly, maybe, blue light blocking glasses, blue light blocking features actually can have an impact because they get your environment at night to be more like that kind of Paleolithic environment that humans originally developed in. So does that mean, though, that you should always wear blue light blocking glasses or that you should always leave those functions on your phone? And the answer is definitely not. So remember, you want your circadian rhythm to be in sync with the environment. You don't want it to your brain to always think that it's nighttime. You want it to be synced so that when it's daytime, your brain thinks it's daytime, and when it's night, your brain knows that it's night. So if you wear blue light blocking glasses all the time, even during the day, you're depriving your brain of the input that it needs to do that photo entrainment process because you're eliminating all the blue light that tells it that it's morning. So if you block out that blue light during the day, you'll actually tend to feel worse. Your sleep will be worse. There's evidence that it can decrease or lead to depression or decrease your mood and cause all kinds of other impacts. So basically, it's all about timing. You want to eliminate blue light at night when our Paleolithic ancestors wouldn't have seen it, but you want to embrace it and bring it in during the day. So according to Harvard School of Medicine, for example, you want to experience as much bright blue light as you can during the day to signal to your brain that it's daytime, to improve your mood and productivity. There's actually evidence that it can make you more productive at work if your brain is being signaled that it's daytime. And the best way to do that is to spend at least 30 minutes somehow exposed to bright sunlight. Obviously, protect your eyes, don't look at the sun, wear sunblock, but go out, take a walk in the morning, or just sit by a bright window. If you can't access that, there's different tools you can get from your doctor that expose you to a particular wavelength of blue light safely. It tells your brain that it's morning. But again, the easiest way is probably just to go out for a little walk or drink your coffee on the patio in the morning and get some of that blue light. And that will signal to your IPRGCs and onto the SCN that it's morning, and that will synchronize your circadian rhythms to the day. And then when you get into the evening, switch on night shift, switch on night mode. Wear those glasses if you want to. Blocks are very expensive, but there's cheaper ones you can get on Amazon, and take those steps to eliminate that blue light so that your brain doesn't think that it's morning when it's actually nighttime. If you want to read more about how to leverage blue light, it's kind of a brain hack to improve your productivity and sleep, check out my piece. Again, it's at debugger.medium.com. Subscribe here or follow me if you want to see more of these podcasts. And I'll also be doing some YouTube videos on my channel about this. So link to the article in the description. Again, subscribe to me here, and thank you for listening.